Hello everyone, welcome to interview preparation session. Just 2 minutes, then we will begin. To interview preparation session. So today we will discuss about regression. So the first question, what is regression? The first question, what is linear regression? Anyone? Okay. In simple terms, linear regression is means that is a method of finding the best straight line fitting to a given data. That is the best linear relationship between the independent and the dependent variables. In technical terms, linear regression is a machine learning algorithm that finds the best linear fit relationship of any given data between independent and dependent variables. It is mostly done by the sum of square residual methods. Anyone understood? Everyone understood or any doubt? Exact list, Ipsita. Now, let's go for the second question. Second question is, can we use linear regression for time series data? Yes or no? And if yes, then why? If no, then why? Answer to that. Please explain your answer. Why we can use? If no, why we cannot use? Okay, okay. The answer is we can use linear regression from time series data analysis, but the result are not presenting the perfect analysis. So it's generally advised to not to use that because the result is not that much promising, that much we want. So it is we can use, but it is not relevant. Okay, the third question: how does multi multicollinearity how does multicollinearity affect the linear regression? Okay, no one is answering. So, multicollinearity occurs when some of the independent variables are highly correlated, that is positive or negative, that doesn't matter, with each other. This multicollinearity causes a problem as it is against the basic assumption of the linear regression. The presence of multicollinearity doesn't affect the predictive capability of the model. So, if you just want to prediction, the presence of multicollinearity doesn't affect your output. However, if you want to draw some insight from the model and apply them in, let's say, some business model, it may cause some problem. One of the major problem caused by multicollinearity is that it leads to incorrect interpretation and provides wrong insights. The coefficient of a linear regression suggests that the mean change in the target value if a feature is changed by 1 unit. So multicollinearity exists. Everyone got it? Actually, a highly effective way of dealing with multicollinearity is the use of VIF. Everyone, I think, aware of VIF, variance in inflation factor. I think everyone is aware of that. Higher the value of VIF for a feature, more linearly correlated is that feature. Simply remove the feature with very VIF value. and retrain the model on the remaining dataset. That's how you can get rid of the multicollinearity. Okay, the next question. Why is logistic regression very popular? Why you use logistic regression everywhere? Uh, that is more you use logistic regression most of the times. That is why it is popular. Exactly. It gives the probability value. Logistic regression is famous because it can convert the value of logits, that is log odds, which can range from minus infinity to plus infinity to a range between 0 to 1. And as logistic function output the probability of occurrence of an event, it can apply to many real life scenarios. It can be applied to many real life scenarios, so it is very popular. And it is the reason that is very popular. Then, why can't we use linear regression in place of logistic regression for binary classification? So, why cannot we use linear regression in place of logistic regression for binary classification? Why cannot we use linear regression in place of logistic regression for binary classification? Yeah, Kritik, that's okay. Minus infinity plus infinity, the range is minus infinity plus infinity. But what is the main reason? The main reason is the distribution of error terms. That means the distribution of data in case of logistic and linear regression is different. Linear regression assumes error terms are normally distributed, but in case of binary classification, this assumes the assumption doesn't hold true. Like linear regression says that the error terms are normal, but in binary classification, the assumption it can be anything, and the variance of residual errors. Linear regression assumes that the variance of random error is constant. This assumption is violated in case of logistic regression. Okay. Next question is the decision boundary linear or is the decision boundary linear or non-linear in case of logistic regression model? Is the decision boundary linear or non-linear in case of logistic model? If yes, then why? If no, then why? My my question means if linear, then why? If non-linear, then why? Explain that. Everything you have to explain. Okay. It can be linear or non-linear. It depends. As the decision boundary, as the decision boundary is a line that separates the target variable into different classes, it depends. In case of logistic regression model, the decision boundary is a straight line. So, and you know the logistic regression formula, right? That alpha plus 1 into 1 plus 2 into 2, that up to k into k. This clearly represent that is a straight line. So logistic regression is only suitable in such cases where a straight line is able to separate the different classes. If a straight line is not able to do that, then non-linear algorithms should be used to achieve the better result. Otherwise, we can use the linear. Got that? Okay, next question, number 7. You all know about Emily. You all know about Emily. What is Emily? Okay, Emily is maximum likelihood estimator. Okay, so explain that. What is maximum likelihood estimator? What is that? Why use that? What is the uses of Emily? Yeah, what is that Emily? We know maximum likelihood estimator. Emily means maximum likelihood estimator. That is the full form of that. I want a hint. I want an explanation of that. If you know, that's okay. If you don't know, I will explain. Okay. The Emily chooses those set of unknown parameters that maximize the likelihood function. The method to find the Emily is used calculus and setting the derivative of logistic function with respect to an unknown parameter to 0 and solving it will give the Emily. For a binary model, this will be easy, but for a logistic model, the calculations are complex. Computer programs are used to deriving MLE and logistic models. As we know, MLE is a statistical approach to estimating the parameters of a mathematical model. MLE and ordinary square estimation give the same result for linear regression. If the dependent variable is assumed to be normally distributed, MLE doesn't assume anything about the independent variable. So when MLE, when the linear regression is dependent variable assumed to be normally distributed, then MLE do not assume anything about the independent variable. Only it will assume about the dependent variable because it is normally distributed. Then you all know about R square value and adjusted R square value. I think you all know about that. Then what is the difference between adjusted R square and R square? Difference between adjusted R square value and R square value. What is the difference? The basic difference. What is the difference between the adjusted R square value and R square value? If you don't know that, just explain what is R square value and what is adjusted R square value. Exactly. MPAV. So what is your name? Full name? That is MPAV is showing. So MPAV answered the correct answer, but let me explain other things. Adjusted R square, just like R square, both are just same, is a representative of the number of points lying around the regression line. That is, this shows how well the model is fitting for the training data. Wait, let me show the formula of the adjusted R square. Mm, Here, here is the formula of adjusted R square, where the n is the number of data points and k is the number of features. One drawback here, n is the number of data points and k is the number of features, and all others are same. But one drawback of that increase with the addition of a new feature, whether a new feature is useful or not. It doesn't matter it is useful or not, but it always increase with that. That is the most uh, common drawback of this R square, and the adjusted R square overcomes that drawback. That drawback will be reduced in the adjusted R square. The value of adjusted R square increases only if the newly added feature plays a significant role in the model. If it doesn't play a significant role in the model, that doesn't mean it will not increase the value. But in R square, it will increase the value. That is the basic difference. Now we can go to the next question. How do you interpret the residual versus fitted value curve? How do you interpret the residual versus fitted value curve? Anyone? Okay. The residual versus the predicted value plot is used to see whether the predicted value and the residuals have a correlation or not. If the residuals are distributed normally with a mean around the predicted value and a constant variance, our model is working fine. Otherwise, there is some issue with that model. The most common problem that can be found in the training the model over a large range of dataset is is het- the presence of heteroscedasticity can easily seen by plotting the residuals versus fitted value curve. So the most common problem in the plotting the curve that is the model overcome with a large number of dataset and the presence of heteroscedasticity can easily seen by the plotting of the residuals but at the fitted value curve. The next question. Everyone, please, if you know the answer, please write it in the comment box. What is BIF and how do you calculate that? What is BIF and how do you calculate that? Anyone? What is BIF? Just tell the full form. What is BIF? Yes, variation inflation factor. What is that? Yes, Ipsita. That is the correct answer. 1 by 1 minus r square. Okay. PIF is variation inflation factor. It is used to check the presence of multicollinearity in the dataset and it is calculated as 1 by 1 minus r square. Then what is robust regression? Anyone aware of robust regression? Okay, Impa. Anyone? A regression model should be robust in nature. That means with the change in few observation, the model should not change drastically. Also, it should not be affected by the outliers. That means when some of the observation change, that model should not change and that should not be affected by the outliers. And it also not to not be much affected by the uh, other factors that is affect our model. A regression model with OLS. What is OLS? The ordinary least squares is quite sensitive to the outliers. To overcome this problem, we can use the WLS, that is weighted least square. Make a note of that. That is OLS is ordinary least squares and WLS is weighted least squares. Wait, I'm writing that. OLS. Least squares. Okay. A regression model with OLS is quite sensitive to the outliers. To overcome this problem, we can use WLS to determine the estimator of the regression coefficient. Here, less weights are given to the outliers or high leverage points in the fitting, making these points less impactful. So, here we use less weights to the outlier or high leverage point in the fitting, making these points impactful. Okay. The next question is, I think everyone should answer that question. What are, everyone should answer this question. This is an easy question. False positives and false negatives. What are false positives and false negatives? Everyone should answer that because that is an easy question. Yes, Empav. False positives are those cases in which the negatives are wrongly predicted as positive. That means, for example, predicting the customer will churn when in fact he is not churning. I think that customer will churn, but the customer is not churning. That means that is a false positive. In the similar way, when a false negative are those cases in which the positives are wrongly predicted as negative. For exact, for example, predicting that customer will not churn, but when in fact he churns. That means that is a false positive. False negative. When we predict that is positive, but in real that is negative. That is called as false negative, but and the vice versa is the false positive. Another question. What is FNR? What is FNR? And FPR. What is FNR and what FPR? Yes, type 1 and type 2 are further question. What is FNR and FPR? Yes, false negative rate and false positive. What is the formula for that? So FNR refers to the negative incorrectly predicted from all the false tables. It is the frequency of incorrectly predicted truth levels. That is FNR. Sorry. FNR equal to Fn divided by TP plus Fn, where FPR. What is APR? APR refers to the ratio of positive incorrectly predicted from all the true labels. It is the frequency of incorrectly predicted false labels. That is the opposite of FNR. So the formula is that FP divided by TN. What is TN? We will discuss in the next question. Plus FP. I think you all got that point. The next question. What is TPR and TNR? Same like this. TPR means the ratio of positives correctly predicted from all the true labels. In simple words, it is the frequency of correctly predicted true levels, where the TNR means The ratio of negatives correctly predicted from all the false levels. It is the false level and predicted negative. So it is the frequency of correctly predicted false levels that is correctly predicted. That is TPR. The formula of TPR is equal to TP plus Fn, and TNR equal to Tn plus Fp. Got it? The next question. Why accuracy is not a good measure for classification problems? Why accuracy is not a good measure for classification problems? Why accuracy is not a good measure for classification problem? Yes, anyone? If anyone know can write, or if anyone doesn't know, yeah, that's okay. Empha, just write no. See, the accuracy gives equal importance to both false positive and false negative. However, this may not be the case in the most business problems. For example, in case of cancer prediction, we have done that assignment in our institute, that in case of cancer prediction, declaring cancer as accuracy gives equal importance. So you got that point. It gives equal importance to false positive and false negative both. So this may not in the case, however, this may not in the case of business problem. For the example, in case of cancer prediction, declaring the patient uh, malignant is more serious than wrongly informed the patient is suffering from the cancer. Accuracy gives the equal importance to the both cases and cannot difference between them. So accuracy, that's why accuracy is not a good measure for classification. Any doubt, you can ask in the chat. Next question. What is the importance of baseline in a classification problem? You all know about baseline. So why we use baseline in the classification problem? What is the importance of that? The baseline is needed and it is important in the classification problem because most of the classification problem deals with the imbalanced dataset. For example, including telecom churn, employee attrition, cancer prediction, fraud detection, online advertisement. In all these problems, the number of positive classes will be very low when compared to the negative classes. In some cases, it is common to have positive classes that are less than 1% of the total sample. In such cases, an accuracy of 99% may sound very good, but in reality, it may not be. Here, the negatives are 99%, and hence the baseline will remain the same. If the algorithm predicts the instances as negative, then also the accuracy will be 99%. In this case, the positive will be predicted wrongly, which is very important for any business. Every toss, all the positive predicted, that means predicted wrongly, an accuracy of 99% is achieved. So the baseline is very important and the algorithm needs to be evaluated relative to the baseline. If the negative are 99%, hence the baseline will remain same. That's why the algorithm predicts the instances as negative and also give the accuracy as 99%. But that sounds good, but it may not be the good accuracy in the reality. That's why baseline is important in classification problem. So that is it for today, guys. Let's meet tomorrow also at same time. You're welcome.